Equilibrium of a rigid body. Good day, everyone. Welcome to Equilibrium of a rigid body. In previous lectures, we studied forces, moments, and their effects on particles and rigid bodies. Today, we will learn how these concepts are applied to determine whether a body remains in balance under external loads. Understanding equilibrium is fundamental in engineering because every structure and machine component must be designed to remain stable and safe under operating conditions. By the end of this lecture, you will be able to develop equilibrium equations, construct free body diagrams, and solve practical statics problems involving rigid bodies. Objectives. In this lecture, we will discuss the equilibrium of rigid bodies, one of the most important concepts in statics. Equilibrium occurs when a body experiences no net force and no net moment, meaning it remains at rest or moves with constant velocity. We will learn the conditions required for equilibrium, how to construct free body diagrams, and how to solve engineering problems involving forces and moments in both two-dimensional and three-dimensional systems. Conditions for rigid body equilibrium. A rigid body is in equilibrium when two conditions are simultaneously satisfied. First, the sum of all external forces acting on the body must be zero. Second, the sum of moments about any point must also be zero. The first condition prevents translational motion, while the second prevents rotational motion. These conditions are both necessary and sufficient for equilibrium. In statics, we assume the body is rigid, meaning any deformation is small enough to be neglected. Free body diagrams, or FBD, is the foundation of solving equilibrium problems. To create an FBD, isolate the body from its surroundings and replace all supports and connections with their corresponding reaction forces and moments. Clearly indicate all external loads, dimensions, and unknown reactions. A well-drawn FBD simplifies analysis and reduces mistakes during calculations. Free body diagrams, FBD. Several important rules apply when drawing free body diagrams. Internal forces are not included because they cancel each other according to Newton's third law. The weight of a body is represented by a single force acting at its center of gravity. Couple moments are free vectors and may be placed anywhere on the diagram. Different support types produce different reactions. For example, a cable provides tension, a pin provides horizontal and vertical reactions, a roller provides one normal reaction, and a fixed support provides force reactions as well as a moment reaction. Equations of equilibrium, 2D. For two-dimensional equilibrium problems, three independent equations are available. The sum of forces in the x direction must equal 0. The sum of forces in the y direction must equal 0, and the sum of moments about any chosen point must equal 0. These equations allow us to solve for up to three unknowns. Choosing an appropriate moment center can simplify calculations by eliminating unknown forces from the moment equation. Two- and three-force members. A two-force member is a structural element subjected to only two forces. For equilibrium, these forces must be equal in magnitude, opposite in direction, and act along the same line. A three-force member experiences three forces. If the forces are not parallel, their lines of action must intersect at a common point to maintain equilibrium. Recognizing these special cases can significantly simplify problem solving. Free body diagrams, 3D. The principles of free body diagrams in 3 dimensions are similar to those in 2 dimensions. However, additional force and moment components must be considered. Depending on the support type, reaction forces may exist along the x, y, and z directions, and moments may also act about these axes. Careful representation of all components is essential for accurate three-dimensional equilibrium analysis. Equations of equilibrium, 3D. In three-dimensional problems, equilibrium requires 6 independent scalar equations. 3 equations come from force equilibrium along the x, y, and z axes, while the other 3 come from moment equilibrium about those axes. Together, these equations ensure that the body neither translates nor rotates in space. The additional equations make 3D analysis more complex, but also more powerful. Constraints and statical determinacy. An important concept in statics is determining whether a structure is statically determinate or indeterminate. A statically determinate structure has the same number of unknown reactions as available equilibrium equations. If there are more unknowns than equations, the structure becomes statically indeterminate and requires deformation analysis. Proper support arrangements are essential to ensure stability without introducing unnecessary constraints. Tips: when solving equilibrium problems, always begin with a clear and complete free body diagram. Carefully identify all known and unknown forces. Select moment centers strategically to simplify calculations. Finally, remember that if an answer comes out negative, it simply means the actual direction is opposite to the assumed direction. This is a normal part of engineering analysis.